So my name is James Aimonetti. I work for 2600 Hertz, and we make Kazoo, which is a distributed telephony platform built in Erlang. So what is Kazoo? Well, it's distributed telephony. So we come from the open source world. A lot of work with FreeSwitch and Asterisk. If you've heard of Blue Box, that was one of our projects from a while ago. But they're all single box, single server concepts. And so we wanted to build the distributed, in the cloud, if you will, but you don't have to, version of FreeSwitch, essentially. And so to do that, we've had to create a layered approach to the different parts of building telephony systems and then applications on top of that platform. And to do that, we have a very event-driven design where a lot of our code is reactive to things happening, like a phone call coming into the system. So some of our requirements, we needed redundancy and fault tolerance, both at the code level with handling individual calls and things like that, but also at the server and at the data center level. Because as we've seen with when Hurricane Sandy hit New York, when Amazon has their outages, entire data centers can and will go down. So if you're not distributed geographically as well, and your service goes down and you provide 911 services and somebody needs to call 911 and they can't, that's bad. So those are some of the design concepts that we've had to think about as we've gone forward with this. We wanted to make it easier for developers to create telephony applications. So we wanted to push concepts higher and higher level as we move up the layers. So you'll see that in some of our work. And then we needed to be able to scale horizontally. We can obviously scale vertically by getting bigger and bigger servers, but we also need, for the redundancy and fault tolerance, to be able to scale horizontally and have it be easy. It should be trivial to spin up a new server in a certain layer of the architecture. So under the hood, real fast, we use OpenSIPs and Camilio as our SBC. If you're not familiar, it's kind of like HA proxy for web requests, but for SIP. But there's also lots of nice modules in it that do lots of good telephony things for us as well. Our primary SIP engine is FreeSwitch. It's where we do all of our media handling. So if there's codec negotiation, transcoding, recording of voicemails, things like that, that's all done by FreeSwitch. If any of you attended the Logger talk this morning, Andrew Thompson wrote a plugin for that creates a C node out of FreeSwitch. So then we are able to talk to FreeSwitch like another Erlang node. So we don't have to do all of the read off a socket and take text and turn it into Erlang terms. We get all the Erlang terms automatically. We use RabbitMQ for our messaging layer. So this helps us bridge the gap of the low-level part of Kazoo, which sits on top of all of the FreeSwitch servers, and then our application layer, which is where things like voicemail and ringing a device and things like that happen. And then we use BigCouch for our long-term data store. Most of the time, you set up a user, you set up their device, you set up the call flow, and then they don't touch it for a year. BigCouch is wonderful for this. We've had some challenges with doing more real-time stuff with it, and so we've adapted to that. But for long-term storage in a distributed manner and having it be operationally very easy, BigCouch has been a blessing for us. We have a lot of sad but funny stories about customers deleting entire databases off the disk, and BigCouch doesn't blink, recovers them fine, and we move right along. So we can't speak highly enough about it. And then obviously Kazoo, and we have two pieces of Kazoo. We've got the low-level layer that sits on top of FreeSwitch called eCall Manager, and then we have the application layer where things actually happen. So here's our layered approach. At the Border, we have SIP coming in from our carriers and from our devices. So when you pick up your phone and you type in a number, it actually sends a SIP request, which if you're familiar with HTTP and a GET with the URL and then headers and then a body, SIP is almost identical, except that it's invite phone number at some realm and then some headers and then potentially body. And then we send responses like 180, 183, 200 OK. Sounds familiar, right? So that's up there, but SIP is kind of a pain to deal with. So our next layer is taking SIP and turning it into our internal format. Joe talked today about having contracts and taking the outside formats and converting it into an internally consistent format. That's exactly what we've done. We have an internal format for these SIP messages, for our commands to do things. And so that's what eCall Manager does, besides the clustering of FreeSwitch. It takes our internal format and gives it as instructions to FreeSwitch, which then becomes SIP messages and things like that. AMQP does the marshaling of our data around, because distributed Erlang is not great across the WAN, we use RabbitMQ to do that by just connecting TCP sockets across the WAN right now. We're still playing with a lot of the HA and things like federation and such for Rabbit, but right now we kind of have engineered it so that we can have a Rabbit in this data center and a Rabbit in this data center, and everybody still can work, because kind of the binding glue is the FreeSwitch server. Distributed Erlang across the WAN it's not great. Across the public internet, the WAN, WAN, yeah. It was, as far as I know, it was designed to be run in a trusted environment, a trusted network, and so making connections between data centers, not ideal. It's doable, but not ideal. And then we have our HTTP, which is where we interact with most of our developers, our GUI. We have REST APIs for doing all that stuff, and then obviously communicating with BigCouch is all over HTTP. So that's kind of the high level what we're working with. And here you can kind of see a potential layout. So you would have your SIP proxies. We try to use like DNS, SRV records, and things like that to do round robining across that. And then they round robin to the FreeSwitch servers, which then we have multiple eCall Manager servers connected to each FreeSwitch server. So if one goes down, one eCall Manager goes down, there's somebody's still there listening, hopefully. Potentially multiple RabbitMQ servers within a data center, multiple application servers, and obviously multiple BigCouch. If you're going to, yeah. Well, so our business model is more on helping you set this up and running it. We have a hosted offering, but it's not our primary focus. So we don't have, we haven't scaled it for real traffic. Carl's done a lot of like SIP-P testing and things like that, and he would have better numbers to tell you. The whole idea is that you can take this and run it on very small commodity hardware. You don't need to buy huge servers to get started. So we run on Rackspace 1 gig instances for all of these servers. So they're very minimal. So it's obviously going to depend on the size of the hardware you want to throw at it. Because in general, the limiting factor is going to be your FreeSwitch servers. So it depends what you want to do. If you're doing a lot of transcoding, it doesn't make sense to run on small instances. You're going to want beefy hardware. But if all you're doing is, bypass media mode, and all you're doing is the SIP signaling, you can get away with virtualized, no problem. Yeah. So our event-driven design, lots of things happen that come into our system and cause things to happen, and then within the system itself with timers and things like that, firing. And so most of our code is reactive to that. And we do have people that like to manipulate the DB directly, which is naughty. But it happens, so we need to react to it as well. All right, so I've given talks about Kazoo at previous Erlang factories. That's why I'm kind of just blitzing through it all, because we wanted to talk a little bit more about sort of the lessons that we've learned with using Erlang to build this platform. We're coming up on 3 years that we've been working on it. So I want to talk about some of the utilities that we've built and kind of how they've evolved. A behavior that has become the cornerstone of most of what we do. How our caching has evolved as our needs have evolved. How we process a call, just to give you an idea of how we structure the application. And then the latest that we're playing with is this tight coupling of both the GinListener and the GenFSM behaviors. And hopefully you guys will learn something and also have feedback for us about where we can improve. So the first thing that we decided was everybody knows JSON, so we're going to use JSON so that the ease of getting new developers invested in our platform would be low. But at the time, Mochi JSON 2 was kind of the only real JSON encoder and decoder module, and they tagged their JSON objects with the struct, right? So you had a 2-tuple with a struct and a prop list to represent an object. Okay, fine. And then all these other JSON parsers came out, and now they're just doing the single tuple with the prop list inside of it. Okay, fine. We knew that we didn't want to do a lot of pattern matching on the JSON objects. We wanted to treat them like a dict, some sort of opaque type. So that's why we created WHJSON, so that we could interact with these decoded JSON objects in an opaque way. And then as parsers came and went and were better or faster or met our needs at different needs, then we could swap them out, but none of the application code would have to change. So that's how we started. It was just very simple things like get value, set value, delete key, things like that. But now that we've had a concerted effort to integrate Dialyzer into our workflow, we have types defined for use in specs, and we've aliased a lot of casting from a data type to a data type, rather than doing a get value, which is then wrapped in a 2-binary or something. And then, as I said, we're able to switch out the encoder as needed. And we actually did the transition from Mochi JSON to eJSON. I think we had like 3 lines of code that we had to change because Carl was pattern matching on the struct format. That was naughty. So when we first started, we had very simple JSON validation where we would iterate. You would set up a list of required keys, a set of optional keys, and then maybe some optional value validation or type validation. But then we decided with this great JSON schema stuff that we wanted to maybe do that instead. So we wrote a validator that would use that spec and try and validate JSON for us. So like any good team, we gave it to our intern to try. So he wrote the first version, and it was bad. I guess I'll pause here for a second because we were talking about it at lunch, but we found we have a rule of 3 that's kind of emerged as a pattern. And I don't know if there's anything formal to this, but we find that on the 3rd rewrite of a component, we get it. That's the time we got it right. So the first time, it's usually very exploratory, very much a prototype, to the point now where we expect to throw away the first version. And it's just kind of to wrap our heads around the problem space. The second version is usually, like if I write it the first time, Carl usually goes in and adjusts and does it better. And then the 3rd time, we actually meet and talk. And then we get our heads around it really well, and we write a really good version of it. And so that's kind of where we are now, where both Carl and I have taken stabs at writing this validator. But I saw that there was another repo that was doing this, so we may just swap it out and contribute to that instead. But it's a very simple API. You pass in the JSON object and the schema, which is also a JSON object, and you get back the fixed JSON object. So like if there are defaults that you didn't define, it'll fill those in and things like that. Or else you'll get a prop list of the key path and the failure message. so that you can report that back to your client. And then this is probably fairly typical, but whutil was our dumping ground for random functions like type conversion, timer offsets. We had to do some stuff with CouchDB that involved encoding and decoding the account IDs that we use, so that got stuck in there. There's like Gregorian to Unix timestamp conversion. There's all sorts of random stuff in there, right? It's the total kitchen drawer. So now we're slowly starting to break those out into modules that are more easily discovered. But if you ever wonder where we're doing something, it's probably in whutil. So as we saw earlier, AIMQP is a very big part of our platform. And so we wrote a behavior eventually to help us in that endeavor. At the beginning, every process that was going to interact with AIMQP used the low-level primitives like creating a new queue, consuming from that queue, binding it, setting up the bindings and all that stuff. All of that work was done on a per queue basis. So each application, if I wrote it, I did it one way. If Carl wrote it, he did it a different way. There was a lot of inefficient use of channels, which are fairly expensive to create and destroy. And so if you had a process that came up, received a message, and then went down, that was fairly taxing between us and Rabbit. So there's just a lot of duplication of effort going on, a lot of weirdness where, yeah. Anyway, it was bad. We were hurting cats with it, and we were trying to figure out why we were having performance problems, why there was stability issues, all sorts of great things. So then we said, you know what? We've got GenServer, and we're receiving our messages in handle info, and then we're unpacking the AIMQP packaging, and then decoding the JSON, and then we're sending it off to the worker. Maybe we could standardize this so that everybody can make use of that. So that's where GinListener came from. It's essentially GenServer with AIMQP-specific handling on it. So in your start link, you send in the bindings, things, queue settings, consumption settings, all sorts of AIMQP-specific stuff. And then what we decided was each of those messages that came into the handle info of the GenServer part of the code would then be spawned into a handler process with certain information provided to it. So that if you needed to serialize back to your code, you could do that. But initially, each request would come in and be spawned into a new process because processes are cheap. This was amazing for our code. It was amazing for performance. Suddenly, our Rabbit utilization dropped significantly. Things were much cleaner. And most importantly, we were able to hide AIMQP-specific stuff from the application code. So now you're not having to know how to reconnect to the broker when the broker goes down, or how to connect to a different broker that's higher priority, things like that. All of that is done for you in GinListener. And so with our interns, getting into telephony, nobody knows telephony that knows Erlang. Surprise, weird. And nobody that knows Erlang knows telephony for the most part. I mean, it's really hard to find that intersection of skill sets right now. And so what we've been having to do is teach people Erlang and then slowly teach them the telephony side. But then to add in AIMQP on top of that has just been a nightmare. So this has been great because now they don't have to worry about it. And eventually I would like to add XMPP and actually be able to use other messaging protocols as well. But GinListener is everywhere. It's very pervasive in our code, and it's great. So if you have patterns, I recommend creating behaviors because it does amazing things for your code, for consistency. It's just great. Do you have any? That's pretty good. WHCache. This is another module of ours that has become quite prolific in our code base. In the beginning, going to Couch, obviously if we can with stuff not changing very often, we didn't feel the need to pay the penalty of the network. So I just created a dict wrapped by a gen server that had per entry TTL, and we basically just cached the JSON objects that we were storing in the database. And that way we didn't have to go there if it was already in the cache. It was great, except that it serialized access. Everybody was dumping their stuff. All the applications were dumping their stuff into the same dict. And hopefully, if anybody has done anything like this, they know how bad it gets on high-performance code. But we did have a very nice, simple API, and it was easy to use, but it didn't scale. So the next step was to take it out of the dict and put it into an ETS table, and now the gen server managed the ETS table, and that was much better. We grew from the prop list into having records that slowly grew because Carl got tired of adding extra parameters to the functions, and so we just wiped it all up into a prop list and put that into a record. And so now we can do much more complex, fun things with the cache entries. But still, the very simple key value set and find and peek and whatnot still worked great. We took it out of the registered process and we starting them on a per application. So now my application has my cached objects and none other, so I can control it better. And we started to do more complex work. So we have this ability to have a user defined in the system, and that user can have multiple devices. You can have your desk phone at your office. You can have your cell phone that your call forwarded to. You can have a SIP phone on your laptop. You can have a home phone, other devices. All of these things, when you ring a user, all of those things could potentially ring and be answerable. So a lot of that work to figure out which devices go to a user, that kind of stuff that we can pre-compute and cache, well, now the cache has been extended to use that as well. We added callbacks so that when an entity was expelled or deleted from the cache, we could run arbitrary code. So things like registrations. Normally a phone would register for, say, 60 seconds. And then before that expiration occurs, they would re-register. And so now you always know where the phone is. If they don't, then maybe they just forgot and they'll register again. But if you suddenly get a whole mass of expired registrations and they're all from the same domain, maybe that site's down, maybe the network connectivity is down. There's a lot of information to be gleaned from some cache entries being expelled. And so this ability to run arbitrary code, we can email ops, we can say, hey, it looks like you're having trouble with your network because 10 of your devices have failed to re-register. So we can it helps us be proactive in that regard. Yeah. But our biggest issue was still that invalidating entries was still problematic. A user would change their caller ID in the GUI, and they would complain that it hadn't updated. And we would tell them, well, wait 15 minutes, because that was the default TTL. And then it'll update. So we wanted to fix that. So the current version, if you're doing things that involve the REST APIs, the database entries, things that users can change outside of the system that they expect to be reflected internally, you can use the GinListener now. Every time something gets changed within the REST APIs, we broadcast out onto AMQP that this document has changed. And so you can actually subscribe for those document changes and immediately invalidate the cache entry so that the next time the caller makes a call, their new caller ID is pulled down, and then things are good. So that's been nice. All right, so call flow processing. So we have this idea of somebody dials a number, what do you do? The most typical use case is ring a user, and if the user doesn't answer, go to voicemail, right? You could also go to a menu, press 1, press 2, press 3, and based on those choices, you have a tree. Okay, pretty simple. When we first started creating the call flow application, we had the CF executor process get started up for the call, and then it would go into these sub-modules like CF user, CF voicemail, and then we would basically have try catches everywhere, just in case the user module crashed or the voicemail module crashed. And so obviously, very bad for Erlang, not idiomatic at all. So now CF Executor is a GinListener, and it spawns the CF user process and hands off the call information, and it proxies all of the AMQP events related to the call. So say you're in a menu and you're waiting for somebody to push a touch tone, CF Executor will actually receive the AMQP message, unmarshal it, get the JSON object out, and then send it to the CF menu process. And then the CF menu just has a small receive loop where they can grab it and then make decisions based on that. So Callflow Executor monitors those processes. If it receives a down, then it moves on to the next module, or these subprocesses communicate back to the CF Executor saying continue or stop. Like if you've reached the end of the call flow, it tells it to stop. And so that's given us we've got rid of a lot of exception handling code, and it's just a much cleaner interface, much easier to work with now. So for an example, on the right, you can see this is what our GUI looks like. So if somebody dials extension 101, it's going to dial Darren. If he doesn't answer, then it'll go to Darren's voicemail. This is the representation in JSON. So we have the first module to be run, the data that gets passed along to the, in this case, the CF user module, and then the children for what should be done next, if anything. We use the underscore, don't know where we got that from, to be the catch-all child. So if CF user, say it rings, in this case, for 20 seconds, if Darren fails to answer his call, then the CF user will get that event, the timeout event, and it will execute CF continue, CF exe continue, which will tell the Callflow Executor, I'm done, but you should keep going. In which case, CF Executor will come to the children, find the catch-all, and in this case, it's going to spawn a CF voicemail process with the ID of the voicemail box. And then there's nothing left to do, so once CF voicemail says it's finished, then the call flow is done, and it terminates as well. Bless you, whoever sneezed. So it's pretty straightforward. The JSON is easy, relatively easy to read. So this is typical for most of our applications. I'm just using the Callflow application in this case. So we have the top-level application supervisor that gets started when you do application start Callflow. This supervisor will get started. It'll create a CF listener. So anything that's going to be interacting with AMQP has a top-level listener for the most part that handles application-specific requests. So in this case, our listener listens for routing requests, which you can't read. But we also have a second listener called the CF shared listener that listens for things like presence, MWI, and other non-routing call flow related events, which, without getting into the telephony stuff, it's just other stuff that goes on related to phones. And then we have the CF Executor Supervisor, which is a simple one-for-one. So very quickly, call comes in, CF listener receives the routing request, and that JSON gets put into a spawned process. Callflow figures out whether it can handle this call or not, because we have other things that handle routing as well. So it may or may not actually know what to do with this call. If it does, it sends a response back down to eCall Manager, and it gets back a win. If eCall Manager determines you're the guy that won, congratulations. When that win is received, that's when CF Executor gets spawned and the call gets processed. And so obviously, you could have potentially hundreds or thousands of CF Executors under this supervisor. So I imagine eventually we'll get to a point where we start sharding the supervisors, but we're not there yet. So this is the latest and greatest that we're still kind of playing with, but it's the tightly coupling of a GinListener and a GenFSM where it makes sense. So in this case, we have call queues, which are, caller calls in, gets put on hold until an agent is available. So you could, the whole idea is that you can handle M customers with N client or agents where N is less than M, right? Everybody's familiar with call queues at this point, I hope. But agents and call queues themselves are very easily modeled with a finite state machine. But we didn't want to throw away all of the AMQP work we had just done with GinListener. So I said, rather than trying to integrate AMQP into GenFSM, we'll just tightly couple a listener process and an FSM process, and let's see what happens. So a lot of what happens initially is that, and I think somebody was talking about this, but you end up with a status or a state or some sort of internal variable within a Gen server that becomes your state, and then you receive events, and you do things based on that state. Well, that's an FSM, so let's actually use an FSM. Oh, so I kind of laid these out differently. OK. So we have a top-level supervisor that supervises all of our agents in this case. And then we have an agent supervisor, which is started as a one-for-all, which means if any one of the sub-processes dies, all of them will be restarted. And the agents is a simple one-for-one of agent supervisors. That's always fun to talk about. Under the agent supervisor, we have the FSM and the listener processes. And so you can see the main states of an agent are, it's ready, I want to call. It's connecting, meaning we're ringing the agent, trying to connect with the customer. Answered, the agent has answered and been bridged to the caller. A lot of call queues, once the agent is finished with a call, they're put into a waiting period so that they can enter notes into a CRM or do whatever. Paused, if I'm going on lunch break, rather than logging out, I can just pause myself and I won't receive phone calls. Or outbound, where I'm making a phone call on my phone unrelated to call queue stuff. So the code becomes very concise. The way you deal with DTMF when connecting versus when answered versus when waiting or paused changes. Routing requests. So if we're in the ready state and we receive a routing request, we know that the agent is trying to make an outbound call. So we go to the outbound state instead. But rather than having to do all the AMQP-related stuff in the FSM, we offload that to the listener. So all the receiving of call events, routing events, things related to our agent and the calls that we're working on get routed through the GinListener, which then spawns into the GenFSM module. And then when the FSM needs to do things, it sends requests like bridge to caller to the GinListener, who then sends the actual AMQP commands to do so.
All of your calls are synchronous?
Are synchronous?
Yeah. I'm asking.
In synchronous? No. So when the FSM sends a command to the GinListener process, it's a cast. And so the GinListener has almost no state other than like agent ID, account ID, things like that. But it just receives something from the FSM process and does it. There's no decision making really other than, inserting my agent ID or something like that. It's very dumb. It just does what it's told. It's very obedient. So the FSM holds all the state about the agent. So it's the serializing point. These guys are not.
So, but does the FSM doesn't wait for, after it performs and through the listener, after it performs an action, does it wait to receive, or just assumes after?
Well, it's like a Gen server, right? Or it's just hanging out. It's not blocking in a receive loop or anything like that. The low-level stuff might be.
End result will be just another event.
Yeah. So as AMQP events come in, the GinListener process receives them, and then spawns a handler for it, which then immediately feeds it back into the FSM. So when I want to ring an agent, so the caller's on hold here, I spin up, I originate a channel to the agent, and then I sit and listen until I get either a channel answered event or a timeout or a reject. Maybe the agent hit reject on the phone. So all of those become events back into AMQP, which the GinListener receives and feeds into the FSM. So if I go from ready to connecting, which is when I'm trying to ring the agent, and I receive a channel answered event, then I move to the answered state. If I receive a cancel or a timeout or something like that, I'll increment how many failed attempts there were and go back to the ready state. And then if they fail like 3 times or some configurable amount, I'll log the agent out automatically.
Where do you store the data, failed data? In the FSM, the state of the FSM?
Yeah, in the state of the FSM. Yeah. But things related to like reporting and calls and all that stuff go into the database. But things specific to the agent process are stored in the FSM. And it's been really nice. I've really enjoyed this pattern. I've applied it to the call queues as well, but the call queues I've made a little more complicated. We still have the queues sup, and then the queues sup. And this is really fun when you were talking about AMQP queues versus call queues versus message queues within the Erlang process. There's a lot of overloading of queue in this. It's great. We have a queue manager, which was necessary because we wanted to be able to process more than one call into a call queue at a time. And so for now, I have a workers sup and a worker sup, and then the FSM with, in this case, 2 listeners, and there are reasons for it. But this works really nicely because call flows will receive a call for the call queue. It'll send an AMQP message, which the queue manager is listening for, which will then do some reporting and metrics and other things. And then it will republish this customer call request, which will then get round robin between these queue shared processes. So they all bind to the same AMQP queue. So you could have multiple consumers, and then these calls will round robin. So that's how we do the parallel processing. So if there are 5 calls, and you have 5 listeners, all 5 will try to connect to agents at the same time. And then you have the QListener, which handles, so we receive the request, it gets fed into the FSM. The FSM then asks the QListener to send events out to the agents saying who can take this call. The agents respond to my QListener process via AMQP, which then feeds it into the FSM. And the FSM has either round robin or most idle or some other strategy to figure out which agent that responded should get the call. Things like that. So anyway, it's really cool. It really cleaned up the code from having just gen servers with a variable in their state. And I don't know, it's been really cool. I really like it. So you should try it. And that's the last slide. How are we doing on time? We're good? Okay. So the project is at GitHub. It's completely open source, the whole platform. We have chef scripts to help with installation, but you can obviously manually install it. All the components like Rabbit and BigCouch and FreeSwitch and OpenSIPs, Camilio, they're all open source. So you can build your own cluster, play with this. We're 2600hertz.org. We do telephony stuff. That's me, James. And we're always unofficially hiring because it's really hard to find people that want to do telephony and Erlang. So you don't necessarily have to do telephony either. We do a lot of other stuff on top of the telephony. So if you're interested, let us know. We're really fun. Any questions? Comments, snide remarks?
So beyond GinListener, any lessons learned with Rabbit?
Yeah, the question was, besides GinListener, any lessons learned with Rabbit? Yes, and that's a talk in and of itself. So Rabbit is wonderful. Like BigCouch, we can't speak highly enough about it. All of the issues have been on our end with abusing Rabbit, like creating channels and queues willy-nilly and really having it was just kind of Wild West shootout. I want a channel, I can have a channel. You get a channel, you get a channel. Everyone gets channels. And creating those channels, once they're created, it's fine. But that whole creation process really is expensive, relatively. And so if you have a lot of calls and they're all spinning up channels at the same time it gets to be quite a bit of load. And so obviously that impacts your scaling. So as we learned better strategies for where we could have a little bit of serialization on creating queues, consuming from those queues, and then multiplexing out into Erlang, we saw a significant CPU utilization drop, memory drop, all sorts of stuff. Our code itself is cleaner. Carl's done a lot of work on sharing connections, doing automatic failover. We have clients that are using stuff, that are using Kazoo in very tumultuous environments where links go down all the time. And so it's not to pat ourselves on the back too much because there was a lot of work involved to make this work, but the ideas that, the theories that we had about how the platform would work held up for the most part. And so we're able to go from 3 nodes completely connected to 3 nodes completely not connected, and then have them come back hours later, and everything's fine. So yeah, it was mostly just us abusing Rabbit and then figuring out better ways not to abuse it. I don't know, what's a...
Yeah, efficient use of the channels and knowing when to protect the connection and let the channel die, or let the whole connection die and go somewhere else.
Yeah, that was another thing. Unbinding a binding that didn't exist would take the whole connection down, which would then, you'd have to reconnect everybody, and you have the stampeding herd, and then it just became a complete mess. Yeah, so we've done a lot of work on our side to insulate ourselves from accidentally doing that, things like that. Yeah.
I have a question coming from web chat.
Okay.
The question is, do you find latency introduced by WebKit acceptable in high-load situations?
At the moment, yeah, it hasn't been the limiting factor for us. The question was, have we found latency issues with using RabbitMQ? For the most part, the requests don't go over the LAN or the WAN, so we're operating within Rackspace's network internally, and so it's usually pretty fast. Well, we do go over the WAN as well, but that's kind of like a failover. So we send out a route request, so it'll go from eCall Manager to the WAPs via Rabbit, but it'll also go to the other data center, Chicago and Dallas, say. So we expect, if the request originates in Dallas, that the Dallas application server will respond first, just because it doesn't have to deal with the network latency as much. But if for some reason the Dallas application server is down, or doesn't respond properly or whatever, then we still have Chicago as a fallback, and maybe we have 100 milliseconds, 200 milliseconds on top of that. But in general, we haven't seen significant issues from it. Not to the point that it's noticeable to users. Most users are used to, even up to a second of pause before ringing starts.
Curious if you're using FreeSwitch pretty much out of the box, or if you've made your own modifications to it.
So we've actually had issues with users with their own installations modifying the XML to configure FreeSwitch, because we try to manage everything in Kazoo, including the FreeSwitch XML configuration. So we don't use standard, like the normal dial plan or directory XML structures or anything like that. We've patched a few things for FreeSwitch, but I mean, we don't really do a lot of bizarre tuning or anything like that. Yeah, we've been doing a lot with the Sophia recovery stuff, if you're familiar with that. So Anthony, the main FreeSwitch developer, they wrote the ability to have FreeSwitch running in an HA. So basically you have 2 FreeSwitch servers, and if this guy is processing calls, it logs it to a shared database, and then they're heartbeating with each other so that if this one crashes, you can actually rebuild the channel on this server and send a reinvite, and then all the calls should stay up, assuming the carrier and all that stuff is involved. So we've taken that and we've applied it to individual channels. So now we can, say you're in New York, and your call happens to get round robin to LA, and then you're calling somebody in New York. So rather than making the SIP and potentially the RTP go all the way across the country twice, we could actually move your channel from the LA box over to a New York-based box. And then you get much lower latency, much better quality audio, things like that.
It's important to know if you do that, like pulling the state out of the server into Kazoo with the state, so you don't need to share it back to anybody.
And we don't use the registration module in FreeSwitch. We store all of that in Kazoo. So if you register to FreeSwitch 1 and a call comes in for you on FreeSwitch 2, we don't have to somehow take the registrations from 1 and put them on 2. We store them in Kazoo, so then we know how to get to your phone from FreeSwitch 2, even though it never got your registration, things like that. But yeah, I mean, as far as like doing weird hacks to FreeSwitch, not really. It's pretty vanilla still.
How much of that preparation is done before the startup, and how much is during the deployment? I mean, all that configuration.
Well, so when eCall Manager starts up, it has a list of FreeSwitch servers that it connects to, and it registers itself for dial plan requests, directory requests, things like that. So if you're familiar with like XML, the XML RPC stuff that FreeSwitch can do, like XML CDR and stuff. So it's essentially like that, except with mod Erlang event, we are able to do that all with native Erlang rather than an HTTP request or something like that. But then from there, all the dial plan and directory is done by Kazoo using either send message or the API commands, like UU, ID, kill, and that kind of stuff.
Thank you very much.
Thank you.